All right, so this is supposed to be a 3 here. But to graph this rational function, you have to remember the first thing we have to do when we did these is you start by looking for your vertical asymptotes. Then you find your horizontal asymptotes. Which, don't forget, for the vertical asymptote, it's all the values of x. Values of x that make your, just put denominator 0, right? And for the horizontal asymptote, it was 3 cases, right? There was 3 different cases we talked about, and it had to do with the degree of the numerator and the degree of the denominator. So whenever the degree, now write degree of numerator is smaller than the degree of the denominator, your horizontal asymptote, your horizontal asymptote was at y equals 0. When the degree of the numerator was equal to the degree of the denominator, you had to divide the leading coefficients. And remember, the b sub n and a sub n and b sub n comes from the leading coefficient on how we wrote rational functions. I'll make a quick note here. For the rational function, it was a sub n x to the n, right, plus a sub n minus 1, and you kept writing it, and it was b sub m x to the m. So this was an m, I believe, that I put. And then you kept writing plus b sub n minus 1, and so on. So when I say a sub n over b sub n, these, talking about the leading coefficients. And then the last case was if the degree of the numerator was bigger than the degree of the denominator, there was no horizontal asymptote. So if we look at this problem, our vertical asymptote is we take our denominator. So we take our denominator. We're trying to find all the values of x, right? Values of x that make your denominator 0. Now we have to start with the GCF, which both of these share an x, which can factor out an x. That leaves us x minus 4 equals 0. And again, this denominator is a polynomial. So it can be 3 terms, it could be 4 terms, right? It could be the difference of squares, difference of cubes, different ways to factor. So you have to go through those techniques. You set x equal to 0. And then x minus 4 equals 0. Now, when you set this equal to 0, I know it just looks like an x by itself, but you still have to set it equal to 0. And then the next factor is 4. So this is my vertical asymptotes are at 0 and 4. Now, for the horizontal asymptote, we're dealing with this middle case because the degree are the same and their leading coefficients are 1 and 1. So that means my horizontal asymptote is at 1. So when you sketch them, again, you have this graph here, you kind of have to make wherever your x and y is. But because we have a horizontal asymptote at 0, I'm going to, instead of making that x-axis, I'm just making a big horizontal asymptote at 0. And then there's another one at 4. Oops, that's 3. So here's at 4. And the horizontal one is at 1. So it's right here. So again, 0, 1, 2, 3, 4, 5, negative 1. Now, don't forget, sometimes we do cross this horizontal asymptote. So we have to set it equal to the horizontal to verify if I have to set the whole function equal to my horizontal asymptote to verify if it will intersect it. So it's going to be here. I multiply by x squared minus 4x to both sides because I'm trying to get the variables out of my denominator. That simplifies on the left, leaves me with x squared minus 4 equals, and when you distribute here, it's x squared minus 4x. Now, when you subtract this x squared to both sides, right, you can't tell if you're moving it from the left or to the right because they're both identical. But because they're both identical, they are going to cancel out when you subtract them, which leaves you with negative 4 minus negative 4 equals negative 4x. We divide negative 4x to both sides, and we're left with 1 is equal to x. So that means I have found a y value and an x value. Right? That 1 comes for my y, and that x comes for my 1. So that is going to be the point where this graph, so at 1 and 1, there's going to be an intersection here. Now, what do I do next? I have to... My pencil's dying. Now I start using my test points, right? So figuring out where are things going to cross and so on, and intersect, and what the graph is going to be. Remember, I use test points to determine this. So I'm going to start with negative 1. So I'm going to do f of, sorry, it's a little big. I'm going to do f of negative 1. That's going to be negative 1 squared minus 4 over negative 1 squared minus 4 times negative 1. That leaves me with 1 minus 4, and then 1 plus 4, which will give me negative 3 over 5. So at negative 1, we have negative 3/5. So that point is going to be about here. Right? Because this would be negative 1, and this is negative 1 for the y, so 3/5. But remember, we know this is the only place it's going to intersect. And don't forget, there's like a little fly or a little mosquito that just wants to, I always like to call these as like the light. It wants to approach the light. Right? Just curves here and curves here. And that's what the graph, I should probably make it much thicker. That's what the graph is doing. Again, I can also plug in 5. F of 5 equals 5 squared minus 4 over 5 squared minus negative 4 times 5. It's 25 minus 4. And then And then 25 minus 20 is equal to 21 over 5, which 5 goes into 24 times with remainder of 1, right? 5, 10, 15, 20, 4 times, and then 1/5. So at 5, the number is going to go up to 4 and 1/5, so it's about here. Because this is 1, 2, 3, 4. Oops, I'm actually, 4, and then a little bit over that. But once I know that it's going to be trapped in here, I just curve it, and it just approaches the asymptotes. And for this intersection, I have to be careful, right? And there's a couple things we have to remember is this is a function, so it should definitely pass my vertical line test. So I know the graph is either going to, because I can't approach the horizontal asymptote infinitely, because if that was true, then it would almost appear like I was going to cross the vertical, which I absolutely can't. So here, the only thing inside these two, it's either going to approach one of these two vertical asymptotes, or two of these four, I mean, from either above or below. So it's either going to touch that point, intersection point, and go up. It's going to approach it here, touch it, and go down. Or it can go through and approach opposite asymptotes. What it definitely cannot do is go through and then approach the same asymptote, because that would fail the vertical line test. And you'd have to use a test point between 1 and 0 and 1 and 4. So let's try choosing 2. And that's going to be 2 squared minus 4 over 2 squared minus 4 times 2. Which in the numerator, it's actually going to give me 4 minus 4, which that's just going to make everything 0. So I know I have a point here, which tells me this graph is going to approach this asymptote. Now, like I said, it either comes down or it either approaches either the asymptote from above or below. But what it definitely cannot do is go back to the other asymptote. And for the sake of time, you do have to choose a point here. I would choose 1/2, plug in 1/2, or a calculator. But for the sake of time, it will do this. You will get a number that's above this horizontal asymptote. The graph go here. All you have to do is plug in 1/2, and you'll notice that that is the graph that you would get. Now, for these polynomials, remember that we had two different techniques. You either factor this with the techniques that you know, or we use our rational zeros theorem, which here there's 1, 2, 3, 4, 5 terms. So the only thing we had that had more than 3 terms was grouping, but it needed to be 4. Hence, this is definitely not going to just be using grouping or the techniques that we learned from before. And one thing to take away is I know my degree is 4. So I know I need to end up with 4 zeros. That doesn't mean they're 4 unique zeros, but I know I have 4 different zeros. There might be multiplicity and so on and so forth. But here, we have to list all possible zeros. Let's not forget our P comes from our 6 and our Q comes from our leading coefficient. So if we look at P over Q, so our 6, we have to list all the positive, negative factors of 6. 2, 3, and 6. And luckily, the only factors for the leading coefficient, which is a 1, is plus or minus 1. Now, when I divide all these, well, it's just going to rewrite the same list. Because normally, if I had more factors in the denominator, I would divide each one of my zeros from the numerator with the denominator. But this would just leave me with a list of 1, 2, 3, and 6. And now this is when we start our synthetic division, which you only use the coefficients of each term, but you have to make sure there's no missing terms. So 4, 3, 2, 1, and 0. I'm not missing any of these terms. Let's say the 17 wasn't here. I would have to use 0 as a placeholder. So that's 1, negative 7, 17, minus 17, and 6. And now we just have to use different test points. We could start with 2. So the first one comes down. You always multiply back with your potential 0. You add vertically, so negative 7 plus 2. You multiply. That gives me negative 10. We add, that gives us positive 7. We multiply, that gives us 14. We multiply, that gives us negative 3. We add negative 17 with 14, it gives us negative 3. We multiply back to our potential 0, right? Constantly multiplying back to that potential 0 gives us negative 6. And bingo, That's exactly what I'm looking for, and now I have my first 0. Now, don't forget, these iterations allow you to continually update. So I'm going to use the same numbers because I know I have now decreased my possibilities by, well, not my possibilities, but I've gone from power of 4, and I can rewrite this into a polynomial with power of 3 or degree 3. But remember, we only stop once we get to a quadratic, because that we can either factor or use our quadratic formula. Now, just because 2 worked, that doesn't mean it can't work again. So I wouldn't cancel it as a future potential 0. You can try 2 again. And if it didn't work that one time, that's when you would have to do this process again. And you can cancel out that 2 forever if it didn't work. So we bring our first number down, we multiply back to our potential 0. We add, we multiply, we add, we multiply, and bingo. Right? And sometimes this takes, it's not always that you can guess the zeros on your first try. It does take some time. So don't get frustrated. It does take a couple tries to eventually find those zeros. But now I know this is x squared minus 2x plus 1. Because I went from power of 4 to power of 3 to power of 2. And there's no GCF. I can go directly to my diamond method, which I take the leading coefficient, the constant coefficient, and we multiply them. But 1 times 1 is 1. I have to think of 2 numbers that multiply to positive 1 but add up to negative 2. And 2 negative 1s will do that. And then I go straight into my factors. And usually I would take the leading coefficient divided to these constants. But since it's a 1, 1 goes into both of them. It's going to stay the same. But this gives me 2 additional zeros. But this is going to give me a 0 of positive 1 with a multiplicity of 2. These all have multiplicity 1, multiplicity 1. So when it comes to sketching, I know that I'm going to go through these zeros versus this one, I'm just going to touch it when it comes to graphing it. Now all I have to do is sketch the graph. So I start by making my axis. I look for my end behavior. Well, I plot all my zeros first. So there's 1 at positive 1. There's another one at positive 2 and positive 3. And because the degree is 4 and the leading coefficient is positive, I know my graph is going to go up on both ends. At 1, it actually only touches the graph and it goes back up because it has multiplicity 2. But at 2 has multiplicity 1, so I'm going to go through the graph. Then come back around and go through again because at 3, it is a odd multiplicity. And this is how you would sketch them each time, right? You're looking for your multiplicities, paying attention to the end behavior, because when it's even, they either both go up or they both go down. This is for a positive leading coefficient. This is for a negative leading coefficient. Now, if it was odd, it either goes up on the right, down on the left. This is for a positive leading coefficient, or it goes up on the left, down on the right for a negative leading coefficient. That's our end behavior. And for multiplicity, when it's an odd multiplicity, we go through the 0. When it's an even multiplicity, we just touch the 0. And then we get to our composition. So let's not forget, this composition means f of g of x. So that means I'm taking whatever g is and putting it inside of my function f. So if we start, here's f. I'm literally gonna, I know g is 2x over 2x minus 1 is equal to, well, I know f of x is x over x minus 1. But instead of writing those x's, don't get those x's mixed up with the x's from g. I'm going to put parentheses there. to show where the x's used to be. And then instead, I am going to replace those with what g is, which is 2x over 2x minus 1. And now I need to simplify this. And how do I do that? Well, my numerator stays as 2x over 2x minus 1. My denominator, on the other hand, I have to try to get my denominators to be the same. And right now the denominator for this 1 is just 1. But to get it to be exactly the same, I need to multiply by this 2x minus 1. And I have to be careful with this negative, because not only do I have to distribute the 1, but the negative distributes with it, which will become 2x over 2x minus 1. And again, I'm just making this fraction in bold to really distinguish the difference between numerator and denominator. And once your denominators are the same, which I'm doing that here, this just becomes one really big fraction in the denominator, 2x minus 1. Remember, distributing that 1 and that negative gives us 2x minus 1 plus 1 all over 2x minus 1. These 2x's cancel in the denominator. Leaves me with 2x over 2x minus 1 divided by 1 over 2x minus 1. And don't forget, every time you divide by a fraction, you have to multiply by its reciprocal. So that will then give me 2x minus 1 over 2x divided by 2x minus 1 times 2x minus 1 over 1. These two factors are identical, and it leaves me with 2x minus 1 for the composition, right? This wasn't asking for inverses, none of that, just do purely composition. Now, these next two, it's asking to check if they are inverses. And remember, the idea of inverse is that if you can compose two functions and it simplifies to x and you compose them in both directions, that means these two functions are inverses of each other. So, but instead of f and g, of course, we're dealing with h and k. So I'm going to start with h of k of x, which is h of k of x. And I will replace that k with what k is equal to, which is x plus 2 over 4. And then this is going to go inside of, well, now I can replace this h with my 4x minus 2. But instead of x, that's where x plus 2 over 4 is, which the 4's will cancel. And I'll be left with x plus 2 minus 2. The 2's cancel. And I'm left with just x, which is exactly 1 that I want. Now I'm going to do it the other way, which is going to be k of h of x. And that's going to be where h goes inside of k, which is going to be 4x minus 2, which will be x plus 2 over 4. And then that 4x minus 2 is in here. Now, if you notice, those 2's will cancel once you get rid of these parentheses because they're not doing anything. And then you're left with 4x over 4, which the 4's will simplify and leave you with exactly just x. And because I got x plugging in both directions, I could definitely say h of x and k of x are inverses of each other. And I'll try to post this video soon.